I can. Thank you very much. So I'm Adrian Woodhead. I'm a principal engineer at Expedia Group. I've been using Hive since the very first open source releases about 10 years ago. I contribute to various sort of downstream of Hive projects that we've open sourced. I'm also the maintainer on Hive Runner, which is a unit testing framework for Hive. So what Peter's referring to, I'll just share my screen. I assume everyone can see that. So yeah, at Expedia, we use Hive a lot, but we've also been very interested in Iceberg, which some of you may or may not know about. So about a year ago, we kind of embarked on a journey of, how could we marry these two technologies together to kind of get the best of both worlds. So that's what I'll be talking about today. So initially, I'll just be focusing on sort of an initial introduction, the work that we did on the Hive read path, and then I'll hand over to Peter, and I think Marton are going to talk about the write path and some other aspects of this. So just very quickly, I'm sure most of you know about this kind of stuff, but typical data lake, you have a bunch of engines which are doing compute and query. So this is things like EMR or Spark or Presto or Hive's execution engine or Tableau. And the way we have it set up is it gets all of its information, all of its metadata from the Hive metastore. So that's the schemas and then all the locations of all the folders inside all the partitions, etc., that may be stored on S3 or some other kind of distributed file store. So that's fine, but when we get to a certain scale, we run into some issues with the Hive metastore. So one of the big ones that we see is the metastore service. That's obviously a thrift endpoint. And it's when you're retrieving information about really, really big data sets, which go back 10 years, and they may be partitioned by hour, for example, you start wanting to be able to get information on tens of thousands of partitions on every query. And you very quickly start reaching memory limits inside the metastore. I think we run our metastores now at like several hundreds of gigabytes of RAM in order to be able to handle these kinds of queries. What we also see, because of the way Hive works, that it stores the partition information or table location information at a folder level. Whenever you're doing query planning, that often needs to list all the files inside those folders. And that can be a fairly slow operation, again, when you're hitting distributed object store in the background, and you've got tens of thousands of partitions with millions of files inside them. Another issue we've seen is the sort of inability to alter your partition scheme. So when you create your data set, your partition scheme is fixed. And if you want to change it, you effectively have to throw away your data set and recreate it from scratch. And what we would like to be able to do is have data sets that for the last 3 months, it's partitioned by hour. Going back 6 months, it's partitioned by day. And maybe going back a year, it's partitioned by month. So we can do roll-ups, which you can't do with Hive today. And then also if you're updating data, I mean, this gets a bit better with Hive on ACID, but Hive 2, which is what we're using the most at the moment, if you're going to update data, you have to restate the entire partition. And there's also all kinds of eventual consistency issues around how you do that in object stores. So Iceberg is a technology which has come along to solve many of those issues. So I'll go through quickly what Iceberg is and some of the features it has, but this won't be an exhaustive introduction to Iceberg. There's plenty of material out there and people are much more qualified than I am to talk about it. But at a very high level, it's an Apache project. It's an open table format. And it was originally created at Netflix for managing huge petabyte scale data sets. It works with any cloud store. You can also use it on-prem with HDFS. And it integrates pretty well with Spark, Trino, Presto, and Hive. So some of the features that are interesting in terms of the sort of negatives I talked about now with the Hive metastore is it actually tracks data at the file grain. So when you're doing query planning and performance, you avoid those listing operations. So that speeds that up. The partitioning isn't as explicit and it can actually be hidden away from end users. So it prevents them making certain classes of mistakes with querying over massive date ranges and so on. You can hide a lot of that from them. You're able to evolve your partition layout over time, so you can have different grains of partitions existing within one table without having to restate all the data. It's got nice features where you can do time travel. So it stores data at snapshots over time. So you can go back in time to a certain snapshot and see your data then and now. And we found that's really useful for being able to do things like model training, where you can version your data sets and train a model with an old version, train it with a new version, compare the results, and then maybe go back to the old version. It's got very flexible schema evolution, and it allows for isolated reads and multiple concurrent writes in quite an easy fashion. So just very briefly how it works, there's a lot more under the hood. Like I said, it tracks data. When you do a write, it stores that as a snapshot, you make some changes to the table, another snapshot, etc. And it tracks all the files in the table over time, and it sort of models that as a linear progression of snapshots where each write produces a new snapshot. So under the hood, it effectively keeps track of these using files. So at the sort of top level, the snapshot will point to a manifest list. And the idea of the snapshot has the list of all the files in the table. The manifest list has a list of all the manifests, and it has a bunch of metrics about each manifest. And then the manifest itself has the list of all the data files and metrics about each file, and then pointers to the actual physical data files. So what's quite nice about this, when Iceberg is doing query planning, it has all of this information available to it, and it can navigate all of that to come up with a really efficient query plan. So what we were looking at to adopt Iceberg is we have a lot of Hive usage, and we were wondering how can we introduce the usage of Iceberg in a way that we can still be backwards compatible with our Hive users so they don't all have to change. So this diagram is a little bit complicated, but the kind of idea we have here is we have a bunch of analysts on the left-hand side who use the Hive API to produce data. So they'll do create table as and that kind of stuff. And that uses the Apache Hive execution engine, and it saves data on S3. What we wanted to do then was enable other users, so like data engineers and data scientists, to use the Iceberg API to produce Iceberg data sets where the data again is stored in S3. And then the missing piece that we really wasn't there when we first started looking at this was being able to read Iceberg tables from Hive. So that would allow sort of early adopters to produce tables in the Iceberg format, but allow all of the end users who are using Hive to still read those data sets. So that is now a feature that's been contributed to Iceberg. So how it works, again, if you go digging around in the code, there's a lot more detail, but at a very high level, it uses the extension points that some of you will be familiar with in Hive. So there's an input format, which is what we worked at. There's an output format, which I guess the others will talk about in a minute. So those extend the standard Hadoop input-output formats, and they integrate Iceberg into Hive's execution framework. So you can effectively execute Hive queries over Iceberg data. There's a SERDI, which does the type conversions back and forth between Hive's types and Iceberg's types. And there's a storage handler, which bundles all of this stuff together and a few other things, just makes it easy to use. So what it looks like as an end user, if you want to use this feature, you can create an Iceberg table. There are a number of different ways of doing that. In this example here, I'm just using Spark with Iceberg has this idea of different catalogs. And the Hadoop tables catalog just stores its metadata on HDFS in this example. So the code here is just standard Spark code where we create a session, we create a Hadoop table, we create it with a schema, some location, we then create a data set, and then we select some information out of that data set, and we then write it with the format Iceberg, and we save it. So that's effectively created an Iceberg table. If we want to then read that from Hive, there is the Iceberg project produces an Iceberg Hive runtime. So you can add that to your class path of whatever Hive tooling you're using. Then this is one way of doing it. You can create a Hive table. So in Hive, you just create external table stored by the storage handler, and you point it at the location. And then you can start querying the data. And it's an Iceberg table, but you've effectively got a Hive table on top of it. So that was the sort of bare minimum we needed to do in order to be able to use Iceberg from Hive. There's some more variations that you can do. So you can actually, when you create that Spark table, you can have it automatically registered in Hive. So you don't need to do that create table step yourself. You can have Iceberg and Spark do that for you. There's also, there's Hive catalog, Hadoop catalog. There's slight variations in Iceberg on how you store the metadata. Some features that we contributed to the Hive read path. There's predicate push down. So the where clause gets pushed down to the underlying readers. So if Park and all ORC and all of those things, if that speeds up the actual queries when they run. Similar with the column projection, again, it'll go down to those readers, which is obviously really good if you've got a columnar-based file format. It supports MapReduce and TES. And all of this stuff, how to set it up and get started with it, you can find it at that URL there, which is the official Iceberg documentation. So that was a very quick blaze through of the read path. I don't know if you want to do questions now, maybe at the end is better, in which case, Peter, I guess you'll take over for the next section.
Thank you, Adrian. I think it was a very good idea allowing you to speak first. So yeah, it was a very good introduction and overview of how it works. Then I would like to share my screen and then I can move forward with the right path. Basically, it's a natural progression of thought that after you are able to read the tables from Hive, then you want to make sure that you are able to write those as well. So basically, this is what we were working. Not share, sorry. I want to present. So what we have been, and I started from the end of the presentation. Nice. So that we were working lately with the guys here. So it is not planned to be as a full-featured view of what we have done, but cherry-picked some interesting stuff we are currently working on or we just finished. So with that, I would like to ask Laszlo if he wants to take over about the catalog stuff.
Yeah, thank you, Peter. Will you mind sharing, and I will let you know when to change slides.
Cool. Okay,
so I will talk a bit about catalogs. So before we get a bit deeper, let me start with a two-sentence summary or recap of what catalogs are for. Catalogs are used to store our metadata about database objects like databases, tables, table attributes, functions, and views. The metadata stored here is accessed when a query is parsed, validated, and optimized. As a consequence of this, only database objects which are registered in a catalog can be referenced in a query. Having said that, in order to be able to use Iceberg tables in Hive queries, we had to provide our own catalog implementation. Fortunately, Iceberg provides an API to plug in catalogs that are used to load, create, and manage metadata about Iceberg tables. Out of the box, it comes with two default catalog implementations, Hive catalog and Hadoop catalog, and a third way, a so-called custom catalog, to allow users to wire in their third-party custom catalog implementation. Let me spend some thoughts about the various catalog types. So first on the list is the Hive catalog, which enables the usage of Hive Metastore to manage Iceberg tables metadata. Using a specified Metastore URI creates a Hive Metastore client, which can then connect to the Metastore. Each Metastore client stores in a client pool and shared between the Hive catalogs accessing the same Hive Metastore. The Hadoop catalog, on the other hand, provides a way to use table names to work with path-based tables under a common location. It uses a specified directory under a specified file system, and which is basically the warehouse. And when we are creating a table, it creates its directory under warehouse directory and puts the table metadata into that directory. Basically, that's it. The custom catalog, well, this is just custom. It can be provided by the end user. One prerequisite here that the loader class must implement the catalog loader interface. And there is a fourth category here, which is named no catalog, and this is used when we don't have any catalog configured, but we have the table location provided when the table itself is created. And then we treat this table as a Hadoop table identified by its location. I've been talking about the different catalog types so far, but let's see how they are configured. Next slide, please. Okay, focusing on Hive catalog, in order to make it work, we have to configure just 4 parameters, all stored in the global Hive configuration. We have the Iceberg.mr catalog, which basically tells us the catalog type. In Hive catalog is obviously Hive. Hive metastore URIs, this is, it's a familiar parameter for all of you who've been working with Hive. It's the Drift URI for the remote metastore. The Hive metastore warehouse there, this is also a commonly and widely used parameter. This is the location of default database for the warehouse. And we have the client pool size, which tells how big is the client pool inside the Hive catalog. Once this is configured properly, Hive catalog should work out of the box. It is easy to understand that after the setup phase, you can access all Iceberg tables using the same catalog. There is one drawback though. When the user wants to use queries accessing multiple tables from different catalog types, this configuration approach will fail. Okay, next slide, please. We have a solution for this. It's called the Hive catalog configuration on table level. That basically the table metadata should be extended with an additional table property, which points to the catalog name. Using this prefix, which you can see on the screen, this iceberg.catalog, tells us the catalog name, and every other catalog-related property should be prefixed with this string. So what we see in this example, we have the iceberg.catalog equals demo Hive catalog table property in the table itself when it's created or altered. And then we define in the Hive global configuration catalog-related properties prefixed with the iceberg.catalog.demo Hive catalog hive.uri, client pool size, I don't know, and so on and so on. Based on what kind of catalog we are using. Yeah. Well, yeah. And after this setup, when the query is executed, involving a table having this table property, and the catalog is about to be instantiated, we collect all these prefix properties and use them to properly initialize the catalog. Yeah, there are some cases when the iceberg.catalog is not defined in the table, then we are fallbacking to the global configuration, and we use the catalog configured there. That is what I wanted to say, and this concludes my part of the presentation. And I would like to hand it over to Marton. Thank you.
Thank you, Laszlo. So hi, everyone. My name is Marton Bud. I'm a software engineer at Cloudera's data warehousing team, mostly working on Apache Hive and most recently on the Apache Hive integration with Apache Iceberg. Next slide, please. So actually what I wanted to continue the discussion with is the DDL support that we created for Iceberg tables. So currently, we support two DDL statements. One is create tables, and the other one is drop table statements. And there's more to come, but this is what we have right now. I'm going to talk about the future plans in a later slide. So one of the considerations that we had to face when thinking about implementing these commands was that basically either for creating a table or dropping a table, we had to touch both the HMS table and the Iceberg table. So it's a two-step process, so it's not sufficient to just create the HMS table itself, but we also have to create an Iceberg table by calling the Iceberg catalog API, which is going to create the initial snapshot for the table, initial metadata. So what we found is that the Hive MetaHook interface, it provides a great way for us to inject some piece of custom code or logic right before or right after HMS calls. So in essence, what this flow looks like is that the MetaHook provides us with a pre-hook and a post-hook. And we can use this pre-hook to check for preconditions or collect the properties that we want to use for creating the Iceberg table or do any sort of change on the HMS table properties. So we do some sort of preparatory work here, and that's followed by the actual HMS call, which creates the HMS table. And then afterwards in a post hook, that's the point in time when we call the catalog API and create the Iceberg table as well, if not exists already. Next slide, please. Right, so I wanted to start with the create table statement. So on the left half of the slide, you see a create table statement, which basically creates a table with two columns, A and B, and also a partition column, C. And we have also specified that it should be stored by the Hive Iceberg storage handler, which essentially it means that it should be an Iceberg table. And so the first thing I would like to call out is regarding the column specs. So here I used an int and the string type, but what should be realized that Hive supports certain types and Iceberg supports certain types as well. And there's quite a bit of overlap between the two. So most of the types that we have in Hive should work out of the box, and they should have an equivalent in Iceberg. But there are some types that are not supported by Iceberg because it doesn't have an equivalent one. So for example, if we wanted to use small int or tiny int or varchar, those by default, they would throw an exception if you wanted to create a table with those columns. But some of these types can be auto-converted to a different Hive type, which does have an equivalent Iceberg type. So for example, if you set this flag for Iceberg MR schema auto-conversion to true, then you would be able to create a Hive table with small int, but under the hood, it would be converted to an integer, which is supported by Iceberg. And there are at least one Hive type, the interval type, which does not have any equivalent one in Iceberg and cannot be auto-converted to any supported type either. Right, so the second thing that I wanted to call out is regarding the partition spec. So here I provided one column C for partitioning, and these are actually translated into identity partitions in Iceberg. So right now we have query language support for only identity partition transforms, but we are also planning to add query language support for other transform types later. And what's also interesting is that under the hood in the Hive MetaHook, these partition columns are actually removed from the HMS table, and they are added to the simple list of columns. So the HMS table actually is stored as an unpartitioned table. And we had two reasons for doing that. One was that basically would throw off the Hive query planner to make it partitioned, because it would look for the data files under the partition directories, whereas the data is actually laid out and stored differently in Iceberg. And the other reason was that what Adrian has already touched on is so it aligns more with Iceberg's notion of hidden partitioning and partition evolution. So whereas in Hive, the user would explicitly have to know about the partition columns, in Iceberg, that's not necessarily the case, and it could evolve over time. Okay, next slide, please. All right, so this is, I think we can skip this for the interest of time. This is basically just a table between the type compatibility between Iceberg and Hive, but I think we already touched this. Okay, so here on this slide, I included a screenshot of what the describe table looks like. So on the top of this, you see the create table command. Again, 2 columns A and B and 1 partition column C. But from the describe output, you can see that all 3 columns A, B, and C are listed on the top in the red rectangle as normal columns, and there is no sign of partitioning. Also in the middle, I called out some other interesting bits and pieces. So the table type is set to Iceberg, storage handler is set to the proper Iceberg storage handler. And because we were using the Hive catalog, the snapshot pointer is also set under the metadata location and the previous metadata location. And the Surday input-output format are also set correctly. Next slide, please. Okay, so moving on to the drop table, which should be much shorter. So this is actually, I guess, a lot simpler. So it similarly to the create table, it uses the Hive meta hook under the hood. So it also allows us to drop the HMS table and the Iceberg table at the same time within the same command. And also if purge is set to true, then it makes sure to delete all the metadata and data files as well. Yeah, next slide, please. All right, so and I'd like to wrap up with the future plans. So there's more DDL to come. First, I'd like to point out the alter table set table properties, which already works. However, if you issue this command, it only updates the property on the HMS table, but it doesn't push down the property change to the Iceberg table. Because basically the HMS maintains its own table properties, and the Iceberg table also maintains its set of table properties. So we need to make sure that they are kept in sync. So the other direction already exists. So if there's another application like Spark that interacts with the same table and they update a property, that property change is already propagated to HMS. So but we need to make sure that this alter table set table properties command also pushes down the property change and makes the sync bidirectional. Okay, the other one that we'd like to develop support for is the truncate table command, and further down the line also adding, dropping, renaming columns. And most of these work will require some extending the meta hook interface with some new methods, because, for example, we are currently missing a post hook for alter table commands. Right, so that's it for me, and thanks for your attention. And Peter, please continue with the right side.
Okay. Okay, given that we are a little bit out of time, I've tried to be a little bit faster. So let's see. So one very important thing we want to do with the table is inserting data into it, because it's very nice to create a table and read from that, but it's a natural need to write there as well. And Hive also has interfaces. These are the interfaces for writing data into the table. Basically, it uses the Hadoop output committer to commit the, so uses the output format to write the data, which creates a record writer. And when this record writer wrote out the Iceberg record object, then the output committer could be used to commit the changes to the tables. So basically what we have here is for one query execution, in case of TAS, it's a DAG. We can have multiple vertices, and these vertices can have multiple tasks, and these tasks can have multiple writers. The writers are the one which are writing the actual data files. And when a task is finished, then the commit task collects all of the writers' data files created by that given task and creates a for commit file for it, from it. And vertex and the query is finished, or once in MR case, when the job is finished, then we are creating an Iceberg commit, which reads all of these for commit files and creates an Iceberg commit for it. Basically, it's introduces the changes or commits the changes to the Iceberg table. Before the commit, the data files are there, but actually those data files are not read by the readers. Only after the Iceberg commit can the readers access the data files, and with this atomic change, we have an atomic change in this way for the table data. Okay, so this table directory layout might be a little bit interesting. This is what you can see when you are list a table directory. You have the temp directory, which contains the query related files, for example, the task for commit files. This temp directory is cleaned up after the query is finished. Other than that, you have the data directory, which contains the actual data files, and the metadata directory, which contains the snapshots, the manifest list, and the manifest files themselves, as Adrian was talking about. So how it works, currently we have a working insert into tables. Then you provide the values itself, or you can use the insert into table with a select command. It's very interesting to understand that while Hive works in a way that when you are inserting the data, Hive creates a temporary directory and puts the data there. And then there is a move task at the end of the query, which actually moves the data to the final place into the table directory. This way, Hive tries to provide atomicity from inserting data, but this thing is failing when you are working on S3, because S3 you don't have the atomic renames. What S3 does in the hood is just copies the data to the final place and removes the old one, which is slow, costly, and it's really not atomic. On the other hand, with Iceberg, with this kind of solution, what you have is you are writing the data files in place. It's there, and the commit is when you are committing the changes to the Iceberg table, and it's atomic and fast. So this is what we have, and we are planning to work on create table as select command and insert overwrite for a table as well, which we had found various problems with the current API. I wanted to show you a demo. I'm not sure. Well, let's try it. I mean, it's not doesn't take too much time, and I think just to show you some things, share. So basically what we are doing here is connecting to our Hive instance, and come on, no. Okay. This means creating a database. We even try to add the C in the beginning of the command. And then we are adding the jar. I renamed that jar here. It's the Hive runtime jar, which is here, but I didn't want to type that much. We are specifying that we are using the Hive catalog. This too is just for us in this deployment. TES AM is not able to connect to HMS, so we moved the committer to the Hive Server 2 side, and this one is needed because vectorized execution is not enabled for Hive for Iceberg tables at the moment. And we have some problems with the fetch task. So here we are creating the table and then inserting into it. And this is the most interesting part of the demo. Okay, so we have run that successfully, and as you can see, we already have the data in place. And just to make sure that it's really an Iceberg table, you can check that the storage handler is set correctly, and we have the metadata location set as expected to the in the table directly in the metadata. So I'm very happy that the demo went without problems. It not happens every time. Okay, and as already mentioned, we run into several problems during the further remaining parts of the integrations. Create table as with the current Hive execution part. It does basically the same way as the insert. It creates a staging directory, and when all of the data is written to the staging directory, then it creates the table, and the final move task moves the data from the staging directory to the create table. With Hive, with the direct insert way, we need a different way of working. We need to create the table in the beginning, and at the end of the insert, we need to commit the changes. Something similar problem we have with insert overwrite. When we are in the writing phase, when we are inserting data, we don't know about whether it will be an overwrite or it will be a simple insert. So we don't know what to do with that. And at the end, in the move task, we have the knowledge of if it's an overwrite or not, but then we don't have the files at hand which have been written. So again, with the current plan execution, we don't have the information at hand which it needed. And Marton has already mentioned several other things. We need query language changes and whatnot. So it is very clear that we will need to have changes in Hive execution, Hive query language to integrate Iceberg in a way that it is useful, it is fast, and the code is clean. So after we initiated a discussion with the Hive and the Iceberg community, and the decision was that until we went through the evolution of Hive 30 and the execution phase changes and such, we copied the existing Iceberg Iceberg and Hive integration code to the Hive repo. So we will have easier time to iterate and move forward with the changes. And when there is a Hive release, then we can decide how and if we want to move it back to the Iceberg Iceberg repo. Okay, so this is what we wanted to talk about. I'm also happy to answer questions and thank you for your attention.
Can I say something real quick?
Sure. Thanks, Ryan.
Hey, hi everyone. I'm Ryan Blue. I originally created the Iceberg project at Netflix. And so you probably see my face a lot if you look into Iceberg, because I've given some talks. Anyway, I just wanted to mention here that a big goal of the Iceberg project, and that I think in the beginning I didn't give enough attention to, is really to be an evolution of what Hive does really well today. So Hive established, the first table format, and really made it so that everyone uses the same layer, the same storage, no matter what you're using, whether it's Hive or Spark or Trino or any number of execution engines. And I think that accomplishment is really huge. That is one of the goals of Iceberg. It's to be the next evolution of what we can do in this space, and achieve that ubiquity. Make sure that we have an open table format that really works for all engines, and enables us to do just a better job of processing. So skipping more data, evolving partitioning in place with tables, and some of the things that people have talked about here. I'm personally really excited about the possibility of really doing a lot better integration between Iceberg and Hive, because I think that Hive is a definitely proven engine with a big history, big install base, and I'm really excited about the possibility for what we can build if we put the two halves of this together. So thank you guys for listening to all of this. Again, we want Iceberg to be a format that enables Hive to get to new places and do better data processing. And the Iceberg community is definitely committed to doing that and helping you guys in whatever way we can. So thanks a lot. I'll shut up now.
Thanks, Ryan. Okay, so Zoli, do you want?
Cool. And then if we don't have any more questions, or do we have any? I was wondering about the thing Adrian have said that it will be possible to time travel, and I was just wondering about how would that be possible to the snapshot files, or?
Yeah, basically, when you have a snapshot files, you have a predefined number of previous changes at hand. So you can decide which version of which snapshots you want to read, and this enables you to time travel.
Okay.